Good day, everyone. This is Abdurrahman Fuad from PetroNile Academy. I'll be your moderator for today's session, presented to you by Mr. Eltayeb Adam. Mr. Eltayeb is an accomplished petrophysicist with over 16 years of experience in oil and gas industry and currently works for PetroEnergy. He earned a degree in Master of Science in Petroleum Exploration back in 2017 at University of Sudan. We are very glad to have you with us, Mr. Eltayeb. I'd like to remind you all that we will be having a Q&A session at the end of the webinar. So kindly write down all your questions for Mr. Eltayeb to answer it. And I'll pass the mic to Mr. Eltayeb. You can start the session.
Okay, thank you, Abdurrahman.
Okay.
Just a little more detail about Mr. Eltayeb. Please let me shed some light and give more information to our listener about our instructor for today. Mr. Eltayeb in particular focused on topics such as like formation evaluation, log analysis, and formation production management. And he had a great contribution to the development of oil field in Sudan, PetroEnergy Block 6. So as Abdurrahman mentioned, because all of our listeners will be in attendee listen only mood, drop all your questions in the chat box and will be answered at the end of this session. So we are highly welcome you, Mr. Eltayeb. Thank you.
Alhamdulillah, I'm very pleased to have this session today, and I would like to extend my appreciation to PetroNile for sharing experience, ideas, and information with young and the graduate student. So for today, I'm going to talk about the formation resistivity logs. Formation resistivity measurement are essential for the saturation determination, as well as we know that the resistivity logs has high depths of investigation. So we are able to get the true resistivity in uninvaded zone away from disturbed zone by drilling fluid. So let's go to the content. So for today's session, we are going to discuss mainly the formation factors that influence and affect the resistivity measurement. First, we will go through a brief introduction to the formation resistivity, and also we will have a brief introduction about the formation conductivity. We'll see the different type of tools just as definition. What's the difference between resistivity tools and induction tool. Second, we will have to consider some theoretical background, and then we will see the invasion profiles and the log response. After that, we have different methods and different way to identify the formation water resistivity, RW, which is the most critical parameter for the water saturation determination. And finally, we will have principal use and limitation. So as definition, the resistivity logs is a measurement of the formation resistivity that is resistant to the passage of an electrical current. And it is measured by resistivity tools. And at least we should get like 3 resistivity curves, like micro resistivity, intermediate resistivity, and deep resistivity. Conductivity tools measure a formation conductivity or ability to conduct an electrical current, and it's measured by the induction tools. So for subsurface measurement, we have two options, either to log the resistivity or conductivity. So the selection of the resistivity or conductivity, this is depend on the salinity difference between the formation water and the salinity drilling fluids. So in general, the resistivity, I would say it will be influenced or affected by three main parameters. One is the water saturation, the second is the salinity, and the third is the porosity. So as we can see on the left side, this is the resistivity response plotted against the lithology profile. So in general, if we have like a porous sand filled with a saline water, in this example, overall resistivity will be low. And if we have at the same formation with the same porosity filled with the fresh water, we will see that the resistivity is a little bit higher compared to the upper one, because change of the water salinity from salt water to the fresh water. So this is one of the parameters that obviously affect the resistivity measurement. The second one, if we take a look at the top of this thick sandstone, which is filled at the top with hydrocarbon, gas, and oil, we will see the resistivity is reading higher compared to the lower one of the water zone. So because this is filled with hydrocarbon, which is not conductive, so we will end up with a little bit high resistivity. So the third effect, it comes from the lithology or from porosity, especially if we have tight sandstone, then we will see very high resistivity. This is the effect of the resistivity. So as I just mentioned, the resistivity will be respond or affected by those three factors. Two of them are fluid independent, and one is the lithology independent. And on the coming slide in this presentation, we will have a little bit more details about the formation affected for the resistivity measurement. Most of the rocks or the matrix are essentially non-conductive, while the other enclosed fluid are conductive. So hydrocarbon are exception to the fluid conductivity, which I would say have high resistivity. When a formation is porous and contains salt water, the overall resistivity will be low. When this same formation contain hydrocarbons, the resistivity will be very high. As we have seen this in the previous slide, the response of the resistivity against the fluids and the lithology. So it is the character that by the resistivity logs, high resistivity value may indicate a porous hydrocarbon-bearing formation, but sometimes be careful, not high resistivity value may indicate porous hydrocarbon. It could be porous filled with fresh water in the formation. So this is some exceptional we can realize from some time to time. So this is the resistivity measure. This is show the importance of the resistivity measurement. Why we measure the resistivity? It is we measure the resistivity in order to identify the true resistivity in uninvaded zone away from the borehole. So it is beyond the borehole, I would say several feet. So this is invaded zone, which is what most important curve. The other curve is the resistivity in the flush zone. This is very close to the borehole, a few inches from the borehole, where the mud filtrate replace more of the fluid in the pore space. So most of the fluid near to the borehole will be saturated with the mud drain or mud filtrate. So we could combine the RT along with the porosity and the RW in order to calculate the water saturation. And finally, we'll be able to compare the saturation in the flush zone with the saturation in an uninvaded zone to evaluate the formation reducibility. So this is just why the importance to have the resistivity measurement. Resistivity is the oldest and still, in many cases, the most important measurement. And we have different types of resistivity measurement, such like focused resistivity devices, lateral logs device, and micro resistivity log, and induction log, and SP log. These measurements need to be combined together in order to obtain the resistivity in an uninvaded zone plus the resistivity in the flush zone. And this will be considered as the main parameter for the formation evaluation. This is a little bit theoretical background about the definition of the resistivity. The resistivity of the substance is the electrical resistance measured between two opposite faces of unit Q of the material. So resistivity has some relation with the area and the length of the area, and the constant of this relation is the resistance measured by ohm. So I have another example also. This is illustrate the definition a little bit more details of the resistivity. So resistivity is the physical properties of substance and it is ability to emit the flow and electrical current. Resistivity is the resistance of the conductive material 1 meter long with a cross-section area of 1 meter square. So the unit of resistivity is the ohm meter. Okay. So in general, the rock is formation is composed of the rock matrix and the pore space, which is filled with the hydrocarbon and the formation water. So we agree that all the dry rock or dry matrix have a high resistivity, very high resistivity because it's not conductive, cannot conduct the current. Also, the hydrocarbon have high resistivity, and the formation water, which is filled the pore space, has resistivity, but the resistivity of the formation fill the pore space is a function of the salinity and temperature. So in general, we see the formation resistivity usually have the reading value between 0.2 to 2000 ohm meter. The resistivity higher than 2000 ohm meter are uncommon. We cannot find it, in our practice. It's uncommon in permeable formation, but are observed in very low porosity formations, such like tide, carbonate, or evaporites. Formation resistivity are measured by either passing the known current through the formation and measure the electrical potential or by inducing electrical current into the formation and measured by its magnitude. As previously stated, as just mentioned before, rock materials are essentially not conductive. However, normal rocks consist not just only of rock material, but also we have a pore space. These pore space are principally filled with water, or it could be filled with oil and gas in subsurface. So the formation conductivity is essentially restricted to the formation water. So the formation water display a very important part in the pore space, because either it could be conductive or non-conductive. So the current flow, it will be subjected or restricted to the formation water more than the matrix. So here we have some variables that these variables influences the resistivity measurement. One of these variables, of course, water saturation. When we have high water saturation, obviously we will get low resistivity. And sometimes if we have low SWI, mean unreusable water with high saturation, we will have or we will get low resistivity, but sometimes it could be oil zone. So we cannot see high resistivity because most of the log just look to the low SWI, high SWI, sorry. So salinity of the water, also this is one of the factors that our variables influence the resistivity. When we have a greater salinity, we will have low resistivity. Greater pore porosity, we will have high SW, and then we will end up with low resistivity. Also, the temperature could influence the resistivity. When we go down, the temperature is increased, resistivity is decreased, and salinity is increased. And the porosity also, it will influence the resistivity measurement. And on the coming slide, we'll see some relationship between the porosity and the formation factor, and how does the porosity will affect the formation factor. The pore geometry or the pore space relation between each other, this is also affect the resistivity too much, as we have seen this in the first example, that the type formation relatively had high resistivity. Also, the composition of the rock, it will influence the resistivity measurement. So still also we have another factor, but this factor, be careful, affecting the resistivity measurement. It's a little bit different than the factors influence the resistivity measurement. So the hole diameter and mat resistivity, bed thickness, and resistivity of surrounding beds. Here in this slide, consider that we have a cube. This cube is filled of water and hydrocarbon at a specific or particular porosity. So the overall resistivity is the function of dry resistivity, or it is the function of the rock matrix, plus the formation water resistivity and hydrocarbon resistivity, and the quantity in which they are present, the quantity, how much the volume of the formation water occupies the pore space, and how much the hydrocarbon occupies the pore space. So the quantity of the fluid also, it could affect the resistivity. But in the practical purposes, the dry rock and hydrocarbon resistivity can be ignored, as because they are non-conductive. So by that, the true resistivity, all the formation resistivity is the function of the RW, function of the formation water resistivity, and function of the porosity and the water saturation. So this is the difference between the resistivity and conductivity. So in subsurface, we have two tests, either we can apply the resistivity, or we can apply the conductivity. So the first test, because it's a direct measurement, which is resistivity, and the conductivity is indirect measurement. So the first test is direct measurement as the current is passed between two electrodes on the logging tool, and the potential drop between them to provide the resistivity. So this is the simple measurement of the resistivity. And for the conductivity, current is induced in the formation around the borehole, and the capacity to carry the current is observed. This carrying capacity is the conductivity. Okay, so in general, this is the difference between the resistivity and the conductivity. This plot shows the relationship between conductivity and concentration of the salt in the solution. As we can see, and on the x-axis, we have the concentration of the solution, sodium chloride, and we have the conductivity for this solution. As we goes from left to right, then we realize that the salinity is increased as the conductivity also is increased. So more saline solution, greater conductivity we can get. So the same formation contain fresh water as the left on the corner. So we have low conductivity, so this is high resistivity. This is the formation resistivity factor. Let us give a small definition. What is the formation resistivity factor? In the rock, the easier the pass through pore, the more current that passes. The expression of this passive behavior of the rock is called formation resistivity factor, usually abbreviated to F, and sometimes FF. When this passive rule of the rock is small, the formation factor is small. When this rock has a large effect, then the formation factor is large. So as we can see here, we have three different formation with the same process. This formation at the top, we have good interconnection between the pore stroke. So we have a good permeability. So the formation factor is low as the current passage is easy. So when we go to a little bit complicated pass of the current on the next rock, or we can see the formation factor is a little bit higher. And also when we go here to more complex pathway of the current, we will get high formation factor. So the formation factor is obviously affected by the grain shape or the connection of the pore stroke. In order to understand the formation factor in the better way, it is useful to examine the influence of the porosity with the formation factor in this cross plot. If you can see on the right side of this plot, we have the porosity plotted in the x-axis and the formation factor in the y-axis, and we can see that we have different rocks in between, and this rocks has a consistent relationship between the porosity and the formation factor. So like sphere rock, and this is rounded rock also has consistent relationship between the porosity and formation factor and this rock. So that means the formation factor has a consist relationship with the porosity within different rock. Also, we can use this plot if we have porosity and you know the rock type, and from that directly you will get get the formation factor. So this is another example. This is log plot for the porosity and formation factor. This is the core measurement for clean sandstone, as established in ash law on a set of rock at lab measurement for wet sandstone. If you look to this plot, we have two lines, and those two lines are fit with the core data. So we have different combination of the coefficient to be fit with the data. So this line, blue line, and continuous line, the equation of this line, F is equal 0.8 divided by 5 over 2. So that means we have two equations. Those two equations depend on the A and M. So here A is equal 1 if it's calculated, it's equal 1, and this is for sandstone, it's equal 0.8, and M is equal 2. Okay. So porosity is not only influence on the formation factor, and the formation factor to the porosity relation, it's variety from one rock to another. But when grain shape is changed, the relation changed too much. So formation factor is therefore strongly influenced by the grain shape. So in geological term, the grain shape is an element of texture, with other factors such like size, grain size, and grain sorting. Then it became a texturally related term, which will be considered in more detail with application of the resistivity logs in studying the texture of the rock, so that we will be able to study the texture of the rocks by using the resistivity logs. Formation factor is usually between 5 to 500. Then higher numbers indicate a greater effect due to the formation. A good porous sandstone will have an F value around 10, while a poorly permeable limestone may have a value around or up to 400. So F formation factor is independent element in the expression of the rock resistivity. That means the F value of particular rock reservoir will remain constant, no matter what the resistivity of the fluid filling the pore space. The F value is therefore constant between the reservoir contain oil and the same reservoir contain water, and we will be able to express the relation mathematically like R0 is equal formation factor multiplies or times RW. So the RW is a wet resistivity, where the resistivity of the water is where the formation resistivity filled with 100% water. So the RT is equal R0, and therefore R0 is equal formation resistivity factor times RW. The formation factor is the ratio of formation resistivity, as we see that in the previous slide, is the ratio of the formation resistivity to the resistivity of the fluid which is contained. When porosity is equal 100%, and this is impossible in the in subsurface, F is equal 1. This is the basic relationship which is used in all calculation involved in resistivity measurement by well logs. So in this plot, we have the relationship between the formation water resistivity and formation factor. And we have 3 rock types here. We have clean sand with lower porosity and clean sand with a higher porosity. And if we realize whenever we change the formation water resistivity in the clean sandstone, the formation factor will keep constant. But if we have excess of the shale in the sand, the relationship will not be linear, or will not goes. We have some variable of the formation factor. Whenever we increase the shale in the sand, we will have different value of the formation factors. This is the relation. This is the resistivity and the invasion. As we know, during the drilling process or during the drilling, the mud filtrate through the permeable formation will invade the formation over certain distance. Because as we know that during the drilling, the hydrostatic column of the mud is a little bit higher in pressure, a little bit higher than the formation pressure. So this will prevent the well to flow, the formation fluid to flow into the well, and also a little bit prevent the drilling fluid not be invaded too much in the formation. However, when most of original fluid is replaced by mud filtrate, we will have invaded zone or flush zone. The invaded zone surrounding the well affect all the logs. Whatever is porosity logs or resistivity logs will be affected by the logs. All the logs within this flush zone, it will affect, especially the resistivity logs. Reading variation around the well are characterized by either invaded zone, as just mentioned, which is a flush a few inches away from the borehole. Transition zone, this is a little bit away from the flush zone, and the virgin zone, we consider this zone is not invaded or is not affected by the drilling muds. Parameters have been defined to characterize the properties of the different zones. So we have some parameters like RT, RW, SW. We have to characterize this parameter in different zones, either it's flush zone or it is an invaded zone. This is the transition zone, which is between the flush zone and uninvaded zone, and this is the uninvaded zone, which we can obtain RT from this zone. Here we can see the resistivity profile representing the radial variation of resistivity caused by the invasion. What we mean by radial resistivity distribution, so we have variety of the resistivity, as we can see here. The resistivity of the flush zone is a little bit high and gradually change to low in uninvaded zone, and in between we have a transition zone. So the resistivity high because the resistivity of mud filtrate is greater than the RW. So at least here we need 3 resistivity curves in order to characterize each zone. So we need micro resistivity, intermediate resistivity, and deep resistivity. This is another example. Show the effect of the invasion profile. Here describe the radial distribution of resistivity from near to the borehole and away to the borehole for some distance. For practical application, a simple step profile is considered or acceptable. This model does not include transition zone. And resistivity and make resistivity like a step change from RXO to RT directly. From distance, RI, from distant RI from the center of the borehole. So that means we have only two resistivity to characterize the micro resistivity in fly zone and the deep resistivity in an invading zone. So here the mud, we consider the mud filtrate is high than the formation water. So because the formation water here is saline and the drilling fluid is high, that means the resistivity of mud filtrate is greater than the RW. This is a more realistic invasion profile, introduce more parameters. For example, this is named Bram profile. Assume that the resistivity goes linearly from RXO at distance R to RT at distance R2, and we have still high resistivity drilling fluid. I mean, the resistivity of mud filtrate is higher and the formation water resistivity is lower. So the resistivity goes from high resistivity and gradually change in the transition zone to the mix of the mud filtrate and hydrocarbon with a little value with formation water, and then goes to the formation water, which is affected by hydrocarbon and some of the formation water. So from high resistivity to the low resistivity because of the variety of the drilling fluid salinity and the formation water salinity. So this is the log response. We have some example of the log response and resistivity profile. In this case, we have water leaving reservoir, no oil, fill the pore space. Only one phase of fluid is water. So we have RXO, low RXO, and high RT because we have high salinity drilling fluid and we have low RW because RT is higher than the RXO. This is the resistivity profile. If we compare all the TVs in the log response, you will see the deep resistivity reading high a little bit compared to the shallow resistivity because the drilling fluid or resistivity of mud filtrate is greater than the RW. This is log response, which is reflected here in the profile, resistivity profile. In some cases, if we have the same value of RXO and RT, that means the resistivity of the mud filtrate is equal to the resistivity of the RW, or the salinity of the drilling fluid is close to salinity of the formation water. And in this case, we will see repeat deep with the shallow, repeat each other, so overlay. This is another example of the normal offshore cases because here we have a little bit high resistivity because the drilling fluid is considered to be with low salinity and the formation water is high salinity. So in this case, we will see reverse. The shallow resistivity is reading high than the deep resistivity. So the deep resistivity a little bit lower compared to the shallow resistivity because of the saline formation water. the formation water lower than the R resistivity of the mud filtrate lower than the RW. Sorry, the resistivity of mud filtrate higher than the RW. Also, we have another example, the resistivity of the drain flow higher or close also to the formation water. You will see overlay, no difference between deep resistivity and the medium resistivity or micro resistivity, shallow resistivity. So this is different also. We have high drilling resistivity of the drilling fluid, which is fresh, and we have saline formation water. So the shallow resistivity is bigger than the deep resistivity. So this is a log response, and this is the resistivity profile. In case if we have water. So when hydrocarbon exists in the system or is present in the system, is a little bit become more complicated. So three phases much more complicated because we will have oil, mud filtrate, and formation water. As you can see here, we have some residual oil with a high resistivity of the mud filtrate and gradually change when we enter to the oil with the mud filtrate and the formation water. So this is the profile, RXO, see a lower, intermediate resistivity a little bit high, and the RT is high because the wall of the oil is exists. So always we will see the true resistivity here is high, and the micro resistivity is getting lower. So when we come to formation water resistivity, as I just mentioned at the beginning, the formation water resistivity RW is important parameter for the water saturation determination. So just here, assume that we have a cube, and this is filled with 100% of the water. The formation always contains some water around the well, and will conduct electrical if it has some dissolved salt. If the salinity is high, it will conduct the electrical current. The formation water resistivity, W, is the resistance of the sample of the formation water with 1 meter long and with a cross section area of 1 meter square at a specific temperature. Other things being equal, like porosity and shale volume and so on. The greater salt concentration we have, the lower resistivity we'll get. This is the concept. So the formation water have a variety from fresh to very saline. Usually they are saline, and the salinity increase with the depths. For oil field purposes, salinity is usually coated in sodium chloride equivalent salinity. Also, formation water brine have a variety of dissolved solid. Seawater has average salinity up to 65,000 ppm, while typical formation brine have salinity around 200,000 ppm. So in this table, we will see some formation water salinity. For seawater salinity, we have range of total salinity, and for the formation water also, we have a range of salinity from saline to very saline, and we have the equivalent RW. Because as we know, if we have the salinity and we know the temperature, then we can calculate the RW. So we have a relation in the coming slide. We can see the relation between salinity, temperature, and RW. So if we know the salinity and we know the temperature of the formation, we will easily get RW of the formation, because RW we need it to calculate the formation water salinity. Yes, this plot I need to show. If we know the salinity, because here from this numbers, we know this is the salinity. If we have the salinity like 2000 ppm, we can go diagonally, and then if we know the temperature, if for example the temperature is 24, we can cross the salinity with the temperature, and then from the cross point we will be able to identify how much is the RW, and then we can pick this RW and we apply in the Arch equation or whatever the saturation equation in order to calculate the water saturation. So this chart of one of the charts of the Sternberger book, this J9, we can use it to calculate or to identify the RW. Also, this is J8. This is as multiplier chart. We can use the two charts together, J9 and J8, in order to calculate the salinity, because if you go back, the salinity on this chart is based on sodium chloride, right? And sometimes we know that maybe the formation water is not sodium chloride. It could be another type of the salinity of different component. Maybe it consists of sodium, magnesium, HCO3, whatever of the component of the dissolved solid that we have. In the nature, we cannot get sodium chloride, but we can get another kind of the dissolved solid. So we can use this chart to convert from another salt component to equivalent sodium chloride component. And we have example for this chart. J9 provide the value of the weighting multiplier to convert various salted to sodium chloride equivalent. For example, formation water sample contain 460 ppm of calcium, 1,400 ppm of SO4, and 19,000 ppm of sodium chloride. So we can enter to the chart J9 with 5.8 as the calcium multiplier and 0.4 as SO4 multiplier, giving the equivalent concentration of the sodium chloride. So if we're doing that, we can get the equivalent sodium chloride. So by multiplier the 4060 is 0.8 and plus and so on, we can get 20,000 ppm. And then we can pick this value and plot it in J9, as we know the salinity, and at the same time we know the formation temperature, and from that we can get the RW of the reservoir. So we have different methods in order to identify the RW. The formation water resistivity can be determined from local tables or local knowledge. And also we will use the well-line information tester sample and take the sample and send it to lab and then get the RW. SP log is one source of we can use it to determine the RW. RT and phi in the water zone. If we have 100% water zone, we can use the deep resistivity, use a process heat to identify the RW, because the RW in the pure water zone is equal to the RT times phi square, or phi over M. RXO and RT tools. Also, we will see this example in the coming slide. From shallow resistivity tool and deep resistivity tool, will be able to identify the RW. So this is one method, is SP log. From SP log, we'll be able to calculate the RW, but be careful, the SP will be used or estimate RW under some circumstance or some condition. First, we have to pick value of the SP of the constant for at least 30 feet. So SP value will be remain constant at least for distance for 30 feet. Second, the area where the SP is constant must be correspond to a clean sandstone. No more shale exists. The value of resistivity of mud filtrate must be remain constant across the same interval. So it will be use the SP with some careful. So this RW determination from shallow resistivity and deep resistivity tool, including bearing formation where the water saturation is equal 1. So where it's full of the water, 100% water. The saturation equation became RW is equal porosity over 2 or over M times RT. We are assuming that A is equal 1 and M is equal 2 in this equation. So this is the second way to identify or to determine the RW. Also, RW, this is another method to identify the RW, determination from RT and phi. After we calculate the water saturation in the flush zone, using this equation, SXO is equal 1 over 5 times square resistivity of mud filtrate divided by resistivity of the flush zone, and the water saturation in an uninvaded zone. So we can divide the water saturation in uninvaded zone by the water saturation in the flush zone, and from that we can rearrange the equation, and RW is equal RT times resistivity of mud filtrate over resistivity of the flush zone. In general, we assume that the water saturation in the flush zone is equal to the water saturation in uninvaded zone, and this is equal 1. So the resistivity logs were used in the following condition. So this is the principal uses of the resistivity. Here is, we need to identify the hydrocarbon. Also, we need to provide basic number of the physical calculation based on the resistivity. Also, can contribute information on the solid texture, as we just mentioned before, flashes, over pressure, and source from aspect. So all this information will be contributed or will be collected from the resistivity. Also for correlation purpose between different wells in the same structure or different structure. So in general, this is the principal use of the resistivity and the conductivity logs, either for quantitative analysis or quantitative interpretation, or semi-quantitative for geology, sedimentology, reservoir geology, or geomechanics. So for main purpose, the quantitative interpretation will be done by the physicists, and we can use this is for fluid saturation of the formation in uninvaded zone. Also, we can use the porosity logs, density anitron to detect the hydrocarbon from the either is gas or oil or so on. So formation water resistivity, RW, is important, mud filtrate, resistivity, and porosity and formation factor and temperature. We have already discussed the relation between the porosity and formation factor, and we saw that how the relation between porosity and the formation factor and what is the formation factor important for the water saturation identification. Also, we know that the temperature will increase and the resistivity is decreased and the salinity will increase against the depths. So finally, this is the limitation. One of the limitations of the resistivity tool can only function in the borehole containing conductive mass that are mud mixed with the salt water. So we cannot run the resistivity tool without, if we don't have conductive mud. They cannot be run in oil-based mud or freshwater-based mud. Induction logs only are most effective with non-conductive like oil-based or fresh water-based. So in order to select, to use or to apply the induction or the tool, this, as I just mentioned before, it depends on the salinity difference between the formation water and the drilling fluid salinity. However, induction logs are also run in the salt water-based mud and are reasonably effective. Although correction the raw reading may be necessary for quantitative use. So thank you. This is all for my presentation, and thank you for attention. And you are welcome if you have any question or discussion. Thank you all for attending this session.
Thank you, Mr. Eltayeb, for this informative presentation. We are waiting to your question. Just let me start with you. Regarding that, you've said the resistivity versus conductivity. I think from the theoretical background, there is a relation between conductivity and resistivity. And to much extent, I can trust to drive or calculate the conductivity from the resistivity log, and how can I trust such answers?
You're right. So from conductivity, you can calculate the resistivity because the conductivity is revert to the resistivity. So from that, and I show this in one slide in my presentation, I have shown this from the resistivity or from the conductivity tool, we'll be able to calculate the resistivity. I show this just here. Let me go to one of the slides here. I mentioned this. Yes, conductivity is generally converted directly and plotted as resistivity on log plot. And from that, we will be able to calculate the resistivity. Is it answer your question?
Yeah, thank you. There is another question said, can we quantify out or find the Vagi porosity with the resistivity log? So if I have a resistivity log, can I calculate the porosity or Vagi porosity from resistivity log? Have you heard my question?
Yes, I got your question well. This time is clear. As you know, from resistivity, we will not be able to get process, because the resistivity is a direct function of the fluid, is affected with the fluid more than the effect with the porosity or fracture or whatever. So only from sonic or from density strong, we will be able to identify the secondary porosity. But from resistivity, we are not able to do that. This is according to my experience so far.
Okay, one more question. Can we calculate, or if there is a specific values between oil and gas zone from logs? I mean, if I've got a resistivity log, can I decide it is a gas or oil just based on the resistivity log?
It will not be easy. Really, it will not be easy to differentiate the gas and oil only based on the resistivity, because we think that the gas and oil both are non-conductive. So it depends on the saturation of the gas and the saturation of the oil, the conductivity will be high or more. But to differentiate between oil or gas based on the resistivity, it's not easy because the gas and the oil is a function of the hydrogen index. And the only curve that will help us to identify the difference between the gas and oil is the neutron, the combination between the neutron and the density. So from that will be it, but from resistivity, it's not easy.
One more question. Ibrahim asked, what does it mean, SXO?
Sorry, could you repeat your question again? I can hear you.
And RXO. Someone asked about what XO. I guess it's an abbreviation, saturation. I don't want to answer the question. He is asking, SXO, what does it mean?
Yes.
And RXO, what does it mean?
Okay. Yes. SXO, this is the water saturation in the flush zone. SXO is the water saturation in the flush zone near to the borehole. And the SW is the water saturation in uninvaded zone. And the SO, this is the oil saturation.
Okay, thank you. One more question. Muhammad asked, could you identify the tool that is used to test the formation and how we can extract the required parameter from the test sample? Have you heard my question?
Sorry, again? No, this time no.
Muhammad, okay. Muhammad asked, could you identify the tool that it is used to test the formation and how we can extract the required parameter from the tested sample?
If I got the question well, you mean that the formation tester, because I mentioned that one of the methods to identify the RW, it is the formation tester, RFT or FMT, and this is the kind of the tool will be place it against the borehole wall and then there is a probe. This probe will be inserted in the borehole and then sucking for sometimes the fluid from the formation and retain this fluid up to the surface. And we can collect a sample, and this sample we consider it is the formation water, and we can take this sample to the lab, and in the lab will be measure the resistivity of the water of this sample, and from that we can get the RW.
Okay. Hopefully that I read all your question. Thank you again, Mr. Tayyib, for this informative, illuminating session, and it was really wonderful. So to all of you, the session will be uploaded in our channel. Until we meet again, bye-bye.